go. Remember to start our recording. This is lecture 17. It's almost the halfway point for the course. This is going to be a topic that we looked at last semester. You remember these words, pointwise and uniform convergence. Obviously, we're going to do it in a slightly more general setting today. But that said, most of this is review. Okay, so we're going to adapt the definitions, kind of the obvious way. Then we're going to remind ourselves of the examples, and but it's going to be mostly review, to be honest with you. Okay, so first thing first, pointwise convergence. Let's define it. So I guess I should say, I think we're in section 3.2 of Tau, because I believe section 3.1 is limits of functions, and we did that back when we did continuity. Okay, and that was the section where we had this really weird definition of a limit of a function, but that won't come up today. Okay. So, right, so I guess I should say we're doing a whole chapter here on sequences of functions. And basically the whole chapter is on uniform convergence, but to motivate uniform convergence, we have to look at pointwise convergence first. So let's have some metric spaces. Have a sequence of functions from one to the other. And our definition is that it converges pointwise to the function f, which we would also want to map x to y, if for every x we can just write it this way. F of x should be the limit of fn of x. Okay. So that's pointwise convergence. We saw it last semester. I think it's a good name for it, right? This pointwise just means look at every point, and for every point, you need to get the convergence. Okay. Now, just as an aside, we don't use the metric space structure on X in this definition at all. X could just be some set. X could just be, there we go, some set. We don't need it actually to have a metric. What about y? Do we need the metric on y here? Yes, Kishav is right. We need that metric so we can take a limit. Okay, so metric spaces are places where we can take limits. And if we're not in a metric space, we can't take a limit. Okay? Now, we know that if this limit right here exists, then it's unique. So if this limit exists, then it is unique. That is a result we proved about just limits in metric spaces. Okay, or actually specifically, I think this semester we just mentioned it. Last semester we proved it on the real line, but the proof extends to any metric space. We would have mentioned it in either the first day or the second day of the semester. Therefore, if you do have pointwise convergence, you've actually got that limit at every single point x. And at every single point x, that limit is unique. So if we do have pointwise convergence, then the limit is unique. So in this case, it's the limiting function. Is unique. Okay, because every value of it is uniquely defined by the limit of the fn's at that point. Okay. Any questions? Okay, what you should remember from last semester is that pointwise convergence is not very good. We'll look at a couple of the quintessential examples here. Let's define Fn to be x to the n. I'll do n at least 1 so that you don't have to worry about what 0 to the 0 is. What's the limit of these functions, the pointwise limit of these functions? Oops. I want to say they're domain and range. Okay, if you've already copied that down, I wouldn't. I'm just going to restart here. Okay, there we go. I want to take the domain to be 0 to 1. What is the pointwise limit of that sequence? Anyone remember? Or work it out right now?
0 over 1.
Uh-huh. So this sequence converges pointwise to the function f of x equals 1 if, well, it's 0, fine. Okay. And this is kind of a problem because all those fn's are continuous, but our limit function is not. Okay, so you can have a bunch of continuous functions, and their pointwise limit, or sorry, they converge pointwise, but that limiting function is not continuous. Okay. So continuity breaks when we just look at pointwise limits, pointwise convergence. Let's look at another example that we saw last semester as well. Let's look at Fn. We'll again go from 0 to 1 to R. But now, we'll define the Fn of x to be, we might not have looked at this exact function, but we looked at something close to it last semester. Fn of x will be 2n if x is between 1 over 2n and 1 over n, and otherwise it's going to be 0. Okay. What is the pointwise limit of this sequence of functions? Should we draw them, maybe?
These like the triangular spikes.
These are not the triangles.
Okay.
So the first one, F1, will be 2 between 1/2 and 1. Okay. The second one, F2, will be 4 between 1/4 and 1/2. Okay. I guess I'll go back to red. The third one will be 6 between 1/6 and 1/3. Okay, then we'll have F4 will be 8 between an 8 and 1/4, and 0 otherwise. Okay. Anyone have the pointwise limit yet?
Just constant 0, right?
Yeah. It's just the 0 function because for every point x, eventually, that 1 over n is to the left of the point, and then your point is just going to be 0. Your value there is just going to be 0. Okay. So we converge pointwise to the 0 function. Okay. And now, and just like the last one where we had a little warning, well, here the fn's aren't continuous. What is the integral of fn from 0 to 1?
Is it 1?
Yeah. Takes on the value 2n in an interval of length 1 over 2n. So its integral is 1. But obviously, I mean, it's kind of stupid to write down. Obviously, if we integrate the 0 function, we get 0. So pointwise limits don't need to preserve integrals either. So we can have the integral from, we can have the limit of the integrals of the fn's is not equal to the integral of the limit of the fn's. Okay. Whenever we write limit of a sequence of functions like this, we mean pointwise limit. Okay. And this is bad because we would like our limits to, if everybody's integrable and has the same integral, we'd like the limit function to also have that integral. Okay? So that's your brief review of the definition of pointwise convergence and the two examples of why that definition is not very good. Are there any questions before we move on? Okay. In that case, let's go back up to this definition of pointwise convergence. Okay, and there's an epsilon hidden in there. Well, there's an epsilon and a capital N hidden in there. Let's make them explicit, okay? So I'm going to just rewrite this definition. And I'm going to write, first we have just the metric space stuff. Let's have some metric spaces. And then we want to say the sequence Fn of functions from x to y converges pointwise to f from x to y if, okay? Now let's unravel this definition. For every x, we have that limit. Okay, and that limit says for every epsilon, there exists a capital N, so that for a little n, at least capital N, blah, blah, blah. So I want to just write that. So this is for every x, and every epsilon, there is a capital N. Now I'm going to subscript it by, I won't even subscript. I'll make it a function of x. The capital N, in fact, we'll make it a function of, how about epsilon and x. Okay, because that capital N is allowed to depend on both epsilon and x. And now we need, what do we need? We need in y, the distance between fn of x and f of x is less than epsilon for all n at least capital N of epsilon and x. Okay. Unless I've made a mistake, that should be the same definition. We agreed on that? Anybody?
Makes sense to me.
Yeah,
Okay.
looks good.
Okay. And now, if you remember back to last semester, again, it's just the same definition, but in a more general setting. For uniform convergence, we're going to move that quantifier on the x. That's all we do. So in uniform convergence, the capital N is not allowed to depend on x anymore. You have to have the same capital N for all the x. What that means is sort of when we write the definition of uniform convergence, we can't avoid putting a capital N in there, like we sort of avoided it in our first definition of pointwise convergence. Okay, so let us put that definition there, and now we're going to write the definition of uniform convergence. And we're going to start with the same boring line about metric spaces. Okay. And we're going to have a sequence of functions. From x to y, but now we are defining what it means for them to converge uniformly. Okay. Now, instead of the for every x, we start with the for every epsilon. And then we need a capital N. Okay. And now we need this thing to be true for every x. And the thing we need is the distance. Okay. So you can see the only thing that changes here is that the capital N isn't allowed to depend on x anymore, because we've moved the for all x quantifier basically inside. However, that little change makes all the difference in the world. Because now, we've got a sequence of functions. Let me make my limit function red. That'll be my f of x. And now you got a sequence of functions. Well, you pick an epsilon. Let me say that that's my epsilon. And now there exists a capital N, so that when little n is at least capital N, all of the functions f sub n lie in this band. Okay, that's epsilon on both sides. Right, so you might have, they might be crazy. But they all have to be in that band of epsilon between. Whereas in the pointwise convergence, that didn't have to happen. Okay, it's just that for every particular point, you had to eventually get there. But here, you have to get there at the same rate, kind of. Go ahead. Sorry.
Could they be discontinuous?
Oh, certainly. Yep. Okay, but it is true. I'll make this SAT style that, let's see, pointwise convergence is to continuity. How do I make this SAT style? As uniform convergence is to uniform continuity. Okay, so that's the analogy here. And you can see it's the same thing as when we did uniform continuity, is we moved a quantifier inside. We moved the quantifier over the point where our delta has to work. We moved that quantifier.
So the main difference between the continuity and convergence is that in continuity we had a requirement on the domain to be a metric space, but for this convergence, as long as it's a set, it works out fine.
Well, they're really different concepts, but you're right that in continuity you need your domain to be a metric space because you need to talk about closeness in the domain, whereas in convergence you don't need your domain to be a metric space because you only need to talk about closeness in the codomain. But it is very different what's getting close to what. When you're talking about convergence, it's the functions getting close to another function. When you're talking about continuity, it's function values. It's values of a single function being close. Okay, but still, this is the rough analogy, is that sort of the way what uniform means in both of these senses is kind of the same thing. Okay, and on the order of the first order logic, you might just think about it as just we moved a quantifier. Okay. What other questions do you have before we?
So previously last semester, sometimes we talked about limits as like a game. Like you give me an epsilon, I'll give you an n.
Yeah.
So the difference with uniform is in the game, I have to pick my n without knowing my x.
Right. Yep.
Okay.
Oh, and I guess we should go back to our examples here. and just point out that last semester we showed that neither of these two examples are uniform. Neither of these sequences converge uniformly to those limits. Okay. Now, that shouldn't necessarily be obvious. You kind of just have to hack around with showing that they don't converge uniformly. Okay, so when you're showing something that doesn't converge uniformly, you pick the epsilon. You argue that no capital N will work by finding a point X for every capital N that you're given. Okay, so those aren't examples of uniform convergence. Let's see, I want to note a trivial, go over here. I want to note a kind of trivial result, but it's worth saying. Maybe we should just make a convention that we're not gonna write this anymore. But anyway, let X and Y be metric spaces. If sequence of functions converges uniformly, well, what I'm going to write is just uniform convergence implies pointwise convergence. If you converge uniformly to F, you converge pointwise to F. Okay. I don't like doing this very often, but I think this one really deserves it. The proof is just trivial. Okay. You just go to the definitions. So you say, okay, if I converge uniformly, then I have this. What does this mean? For every epsilon, there is that capital N of epsilon that works for every x. Well, then you go over to the pointwise definition. For every x, you need a capital N that can depend on epsilon and x now. Well, you just take your capital N from the uniform convergence, and it works. So if you have uniform convergence, you have pointwise convergence. Remember what we said from before. If we have pointwise convergence, then our limit is unique. Okay, so let's say I give you a sequence of functions and I say prove that it does not converge uniformly. So let's say you have that problem. Suppose you want to show that the sequence Fn does not converge uniformly. Okay. Well, these two things combined, show you how to do that. The first thing you would do is step one, compute the limit. Compute the pointwise limit. So compute the limit of the FNs. Okay, what do I really mean there? I mean compute the pointwise limiting function, which is this function. That's how you define it. F of x is the limit as n goes to infinity of fn of x for every x. Okay? And now, if this thing doesn't exist, okay, you're done, because if your sequence did uniformly converge to some function, it would pointwise converge to some function, and that function would have to be this one. So if this one doesn't exist, then you don't have uniform convergence, for sure. If f of x does exist, this is the only function your sequence could converge to uniformly. Okay. So what I'm trying to say here is that these two facts, even though both were trivial, they combined to give us some useful things when we're dealing with uniform convergence. Okay? They also show that, even though we started out by saying that pointwise convergence isn't any good because it doesn't preserve anything that we care about, we often have to consider it. I mean, we have to start with it because we have to know what are we actually converging to. And that's where we look at pointwise convergence. It's easy to compute the pointwise limit, usually. And then if we're going to converge uniformly, it has to be to that function. Okay, so again, even though pointwise convergence isn't a useful property, we frequently do compute the pointwise limits, just as a stepping stone. Okay. Questions there? I guess we should do an example. Let's stick to the reals. Fn of x, let's just make it x over n. Okay. Then the sequence Fn, we should probably say that n is at least 1. This one really does converge uniformly. To the 0 function. Okay, and again, what I was saying right before this is, if you're in any doubt about what it could converge uniformly to, you take the pointwise limit. You see that at every point, as n goes to infinity, we're going to 0. Okay, let's prove that this is really true. Okay. So, what would we do? We need to consider every epsilon, so we'll let epsilon be arbitrary. Okay. Now we want a capital N, it's allowed to depend on epsilon. I'll do this over to the side. We want capital N so that we're in R and our distance is just the normal one. So this is less than epsilon for all and at least capital N and all x in our domain. Okay, what should we do for capital N to find that?
One over epsilon.
Yeah, probably an Archimedean principle too, right? So let's see. We're not actually allowed to choose 1 over epsilon, but we can choose it to be at least that. Okay. So choose capital N to be at least 1 over epsilon. Then for every n at least capital N and x in our domain, we have x over n. I guess we want to compare, we want to take the distance between fn of x and f of x, but our limit function is just the 0 function, so it's just the distance between x over n and 0. Okay, this is at most 1 over n, because the largest x could be is 1 in our domain. Okay, and now n is at least capital N, so this is less than or equal to 1 over capital N. Okay, and now we see we actually want a strict less than epsilon. Right, we want to get that this is less than epsilon. So since we want that to be strict, we go back up here when we chose capital N. We actually want that to be strict. Is that okay? I want to make 3 changes to this example, one at a time. What if we change our domain? Instead of 0 to 1, we're going to go from -1 to 1. Do we still have uniform convergence? And what do we choose as our capital N? What changes in our proof? Yeah, just the same proof. We're going to end up with this absolute value of x over n. That's going to be at most 1 over n. We just need to change right in here, right, our domain changed, so we should change our domain there. Good? That's the first change. Second change, what if we changed our domain to actually like a minus capital A to a capital A? Now what changes in our proof?
what we have to do is, since we have a supremum here, we can just add this constant in, because the absolute value is always going to be, like, we're always going to be, the absolute value of x is always going to be, you know, less than, so we can just pick, we can pick based on the a, but not based on the x, but x is going to be bounded by a. So we just change, our n a little bit.
Yeah. Go back up here. Just choose n to be at least a over epsilon and we're good. Okay? So that's pretty cool, right? We've got uniform convergence on any closed and bounded interval. Final change. What if I want my domain to be all the reals?
It doesn't look so good here.
No. Doesn't work.
My intuition wants to say that we want our domain to be compact, but that's maybe something to think about more and try and prove later.
Yep, I'll let you think about that more. But let me just note that if we change our domain to be all real numbers in this example, not only does our proof not work, but you can show that we don't have uniform convergence. Okay, and again, it's the same kind of thing. If we did have uniform convergence, we would have to converge to the zero function. But you can go through it and you can see actually that no capital N will work. Because for any particular capital N you choose, there is some point x where you're not going to get this less than epsilon. Okay. You probably choose, it's like x greater than n over epsilon or something probably. Okay, I mean, you don't have to guess at that. You can solve the inequality, but I will leave that to you. And have a great weekend. I will be posting, we have one more homework today that I'll post it today. It's due on Wednesday. And then after that, we've got a week off where we don't have any homework or quizzes. Okay, so have a great weekend. I will see you back on Monday.